What's wrong with you? What? You look like you're up to trouble. Ah, the two of you. Troublemakers. It's just a natural way you look, that's all. Current carrying conductor in a magnetic field. Yeah? Yeah? Okay. Let's continue. So, a couple of formulas to look at. We know this situation because we've looked at it using our left hand here. When you have a current, a charge, and a magnetic field, you get a push, a force. And we know this, and we can calculate the force. It's equal to QVB. So we know what the force is, QVB. So remember that a charge moving in a magnetic field will experience a force. What about current? Well, yeah, current as well, because a current is just Q per T, no difference. So let's figure out what the formula is if instead we know the current. So let's think about this picture now. So which way do you want the magnetic field? Into or out of the page?
Go away.
Out. Okay, we'll go out this time. So it's coming out of the page here. Right, which way do you want the current? Left or right? Up or down?
Right.
Okay, so we'll put our current going to the right. So let's just draw it here. Inside the magnetic field. Okay, so this is our I. Right, so which way is the force here? Well, the B is out, the I is right, so the force? Down here. Yeah? So there's a force pushing it down here. So there's an F going down. Let's calculate this F. Well, that's going to equal to QVB. But this time, the Q is not a Q, it's a current. There's lots of charge moving along here. Like lots of little charges moving. So you actually know from electricity that I equals Q over T. So it means you can say, oh, so that's fine. Then I can just say the Q, which I don't know, is IT. Alright, so that's going to be ITVB. Now, let's imagine you know the length here, the length of this wire. We'll call this L. If you think about it, it's a little bit like the distance, speed, time triangle, okay? You know the distance. What's the distance? L. You don't know the speed, but what letter do we use for speed in this question? It's V. And we'd like something about the T. And what does the T equal? L over V. So this would be IL over V, B. But you can see here nicely that the V's cancel. So you end up with this formula in the end. That F equals B times I times L. Bill. Yeah? So the idea is, if you have a length of wire, and it has a current I, and you know the current and you know how long the wire is, then you can work out what the force on the wire is. It's equal to BIL. And this comes from this formula that we did last time. So we can get this formula here. A short little proof, if you can write this down. I don't think so. Although it's not really that crazy. Yeah?
What is the difference with the formula for QVB? Is it the one with the particle?
Yeah. It's barely a difference.
L is the distance of
The length of the wire. Yeah. Sleepy? Everybody looks sleepy.
higher.
Busy day?
Yeah.
Why? How many hours of chemistry did you have?
3 hours.
Oh.
Actually 2 hour
Awesome.
half.
Here, let me help you swipe up.
Careful.
Is it
No, better.
It's better.
Air.
It's not fresh air.
Fresh enough.
Cute. Cute.
Very cute, isn't it?
Is it enough?
We'll see. There.
Oh.
Okay. Continue. What? Air conditioning.
I don't think they can feel it because I barely feel it here.
They're tough. They'll be fine. Don't worry about them. Yeah. What's wrong? It's on. Don't worry. It's on. See, it's moving.
Is there an air conditioner in Ireland?
Yeah. No.
No.
No. Okay. You got this? Yeah. Okay. So we have the formula built. Nice. Okay. In this formula, the current is perpendicular to the field. If it was not perpendicular, what if it was at an angle? So in this formula here, if I just go back over here, here's our magnetic field, and here's our current. Okay, and maybe actually I'll just draw it from a different picture. I'll turn it around. So let's say I'll just draw it like this, for example. There's B, and there's I. Now, what way is the force here? F, B, yeah,
Like that.
into the page. Yeah?
Yeah. Right.
Yeah, into the page. Okay, it's very important that these are 90 degrees, because for your hand, for it to work, all these angles here, these are all 90s. Okay, so what do you think we could do if it wasn't at 90? Let's say instead we put it at an angle theta. We put it like this. What do you think we could do? So instead we make an angle now. Theta. What could we do? Yeah, well, we could look at the two components, right? So we could have how much current is going this way. That would be I cos theta. And how much is going this way? I sin theta. Now, we don't actually care about this one. Why not? Yeah, it's parallel to the magnetic field. And I said the angles have to be 90s. So you realize the only difference if you have an angle theta is in the formula you now have cos theta. That's the only difference. So if there is a theta, we just have this. Now actually, the reason it's sine is because I think I put my angle the wrong way. The current is perpendicular. Oh, sorry, yeah. So we usually measure, I have that backwards, we usually measure the angle this side. So this one is the cos, and this one here is the sine. Yeah. We usually measure the theta so that theta is 90 when they're perpendicular, which is what we want. I'll draw that again for you. Sorry, it's a bit unclear. Okay. This way is B, and then I'll put it to the, this way is the I, and we measure the theta here. So this one here, I cos theta, we don't care about. It's this one here, I sin theta, that we care about. So the formula now is F equals Phil sine theta. Okay, if we can add that formula, please.
Equals field has to be perpendicular
Yeah.
to the
The current and the field have to be at 90. If they're not at 90, if they're at theta instead, we use this.
This finger or this finger?
What?
90 means this finger is 90 or this finger is 90.
That second one.
Second one
This here is 90.
is 90 and
Around like this.
this is
And this is
90.
90. And this is 90.
Okay.
Yeah? Do you have this continue? Yeah? Continue? I'm continuing, so. Right. If a force acts on a current in a magnetic field, then could we use this force to do work? Yes, we can. So, have a look at this picture before we draw or write anything. So let's have a look at what's happening here. It's a very simple machine. So, this is a magnet, okay? Goes from north to south. Right, so FBI, the B is to the left. Should go on the other side. Makes it easier for my hand. The B is to the left. Okay. Now, here's a little battery. Okay. The current comes along, enters here, comes along, goes along here. So the current is going into the screen. So, B that way, I that way, F up. So there's a force on this wire. This wire has a force going up. Now let's look at this side. The current is coming to you. So, B this way, I to you, so the force down. So what do you think will happen if there's a force up and a force down? What will happen to this? It'll rotate. And this is how an electric car engine works. An electric engine. Yeah. If you have a little toy car at home, electric one, it'll just be something like this. It's called a DC motor. Now, the connection here is very important. These are carbon, usually carbon, a little brush. Now, if I have, hang on, let me finish this first before I use it. Okay, so this is the wheel here. Here, make yourself helpful. Hold this there. Okay, you have the two brushes, and there's one on each side. So if you turn this, don't worry, turn? Yeah, the brushes just stay in the same spot. They're just brushing against it. Now, I hope you're clean. Sorry. No, it's okay. I got all the paper here.
Oh, I have the.
No, it's just a student's coursework. It's not important.
Yes, yes, I have.
There, it's fine. No, it's okay. Yeah, it's okay. It's only Jerry's. It's fine. Now, why do you think you need the brushes here for connection? Why can't you just connect the wire to the wheel? Why do you need a brush against it? Why can't you just connect it? Yeah, what would happen? Huh? Twisted, yeah. So if you had the wheel and the wire was connected, then as it turns, the wire would twist and get stuck. So if you have a brush, it can just keep turning. And also, you see this little gap here?
Yeah.
That's important. Why? Yeah, you must have the gap here because you don't want the current just to do this.
Yeah.
Okay, you want to force the current the long way. Yeah. So this is very simple. I mean, this was when was this first used? Maybe like 1880. You're talking like 100 nearly 140 years ago, maybe. You know, in London, you know, the Underground, London Underground, the subway, it uses electric motors. I mean, the London Underground opened like 100 years ago, and 100 years ago it was using electric motors like this. It's very old technology.
100 years ago.
Yeah, something like 100 years ago. Yeah, it's very old technology, but I mean it works. You just need a magnet and a current, and that's it. You can make the wheel turn. Yeah. So, good news is, they sometimes ask students to draw this in the exam.
Throw this exam.
Yeah. So, just to give you some of the words before you draw. This here, and you do need these words, okay, because in the exam, sometimes they don't ask you to draw it. They give you a picture, and they might say, what is this called? You know.
The gap.
Yeah, well, this wheel here, this is called the commutator here.
The both thing.
The wheel, yeah, the both of them. And these are called, obviously, the brush. Well, that's easy. The brush is usually made of carbon.
Why is it made of carbon?
Carbon's a good conductor. It doesn't have to be carbon. It could be something like I guess you could use copper, but maybe you don't want to use something that might make a spark, you know, cause a fire. So I think the advantage of carbon is two advantages. It doesn't spark, because if this is made of copper, it would get like scratches and sparks. And also, it would wear down quite evenly. So after maybe, I don't know, a year, you can just click a new carbon brush on it.
But then it's a good conductor.
It is. Well, I mean, you know, carbon has many different forms. So there's the form that carbon takes in your pencil. What's that called? Graphite.
Yeah.
That's a very, very good conductor. Very good conductor, yeah. And this piece here, that's called the armature. Yeah, the armature. Okay. Draw this. Draw it beautifully, please.
How could you draw this?
You can.
It is 3D.
3D, yeah, 3D with the glasses, yeah.
What does it mean that DC?
Oh, DC means direct current. The other one we'll look at later is Marvel motor.
Marble?
Marvel motor. Yeah.
That is MC?
There's something like that, yeah.
Draw this.
Actually, the fan, the motor inside that would be just like this.
DC motor?
Yeah, it would be, yeah. Hard to see, Bruce?
Yeah, I can see some more.
Can you see on your phone? What word do you need? All of them?
Yeah.
Huh.
What you everything.
Okay, well, can you draw it first and write the words later?
Okay,
Oh, you did? Good, okay. Shamsa, can you see the words?
Yeah.
Maybe you can show them your picture. What is it, Sean, say you're studying next year? Huh? Geophysics. You know you can't wear such nice clothes when you're out in a field, like scooping up dirt. You know this, don't you? And you want to do this. It's so dirty though, no? You're going to be covered in oil. Okay, fine, okay. Alright. Okay, that's true. You drew it? What is that? Show me this picture.
It's more.
Oh,
Good, nice picture.
yeah. Sure.
That's true. You
It's
agree?
okay. Let's see yours.
Why?
Yeah, go on, let's see it.
It's not 3D. 2D.
2D. Yeah. Alright, continue? No, still draw on. Okay.
Artist.
Finished? Let's see your picture. That's like his, 2D, yeah.
Is it okay to draw 2D in exam?
It's okay. Okay. You got it away? Cool. Are we just waiting for you? Audrey, you have it? Almost, okay.
What's the armature mean?
It depends. Like the fan there, it's probably just plastic. Oh well, I mean there has to be some conductor inside of it, but I'd imagine it's probably covered in. Well, actually, I think it would have to be covered in some kind of plastic for safety.
So you mean like the outer
Yeah.
plastic and inside is the conductor?
Yeah. I don't know. My teacher he made one in the lab. We just used copper, but copper's kind of expensive nowadays. You might want to use some alloy, some cheaper alloy. Copper's quite expensive. It's quite expensive. Yeah, copper. I mean, people in my last hometown before I moved, people broke into the church to steal. You know, in the church they have the copper, like the cups and all the religious items. They're made of metal, copper sometimes. People broke in just to steal it, so they could take the copper. They would melt it and sell the copper. Yeah, so I mean, it's expensive enough. It's worth somebody breaking into a church to steal. Do you know? Not good. Not good. And when they're building roads, my teacher told me this before. When they're building roads, they would turn the lights on before the road is open. Now, why do you think they put the lights on before the road is open?
So hard.
What might be the reason for that? Yeah, but if there's nobody driving on the road and the road is closed, why bother having the street lights on?
You want to steal?
Maybe. Well, why would they not steal? The reason they put the lights on is because if they don't put the lights on, somebody will pull all the copper wire out from the street lights. But if it's on, they'll electrocute themselves if they try to do this.
And they can wear rubber gloves.
No, these types of people don't think that level of detail. Yeah. So the copper is expensive. It's quite expensive. Okay, did you draw that now? Yep. Right, so next we want to work out the torque, the turning force. So if we were to look at this picture, yeah, here's the armature, and there's two forces, one this way, and one this way. Now, does anyone remember the name of this picture?
Copper.
Couple, isn't it? And do you remember the formula for the turning force?
FD.
FD, where this is the D. Okay, but we know what F is, don't we? What is it? Bill.
Yeah, here.
Now,
Here D.
what's L times D? Well, look at the picture. We're calling this side here D, and this side here is L.
Oh, area.
So it's the area, isn't it? So this will equal BIA.
Yeah.
Now it gets better.
Yeah.
And finally,
Is it?
sometimes what they do to make it turn more is it's not just one wire, but maybe it goes around like say 10 times and then comes out. So what do you think happens to the force? Well, you have 10 of them.
Yeah.
So if it loops n times, then you just have to stick in an n.
Yeah.
Yeah, oh no, this is how you'll remember. So the turning force, the torque, is equal to I-ban. Yeah. Yeah, just like the bank, yeah. So if you want the turning force here, the torque, it's I-ban. Yeah. Okay, I think it's worth writing this little slide notes down.
Is there any relationship with it, with Leroy-ban? With them?
No,
No.
no.
Just help me to.
Help you to remember, yeah. Now what happened was one year I was teaching this, one of the students noticed, oh, the letters spell I-ban. I'm like, oh, that's a good trick, I'll remember that. Yeah, I-ban. Yep, you do. Torque and electricity, yep.
What letter do we use for moment?
I don't know, like, sometimes I see L used, L, but sometimes I see this Greek letter tau used. And I don't know, I want to try and get into the habit of using L, because I think that's what they use in the A-level books, but torque, the tau is stuck in my head because tau for torque, you know, the T sound, you know. Whereas L doesn't really, you know.
A-level physics is same with this.
No, the A-level has much more in it.
Much more in it and the hard.
Not that the questions are harder, just that there's a bigger syllabus, you know.
N is the number of wires.
Yeah, with number of loops. Number of wires, yeah. Because what you can do is if you have your armature, you can wrap the wire around it a few times before you connect it to the brush. So like imagine these two ends connect to the brush. We picture one wire, but why stop at one? You can just wrap it around a few times, and so it's number of loops, number of turns. Okay, yeah?
But when you change the turning force, it looks like if you loop it, isn't like the length shorten?
No, the length is the length of one of the sides of the armatures. If you loop it more, if you have more N, then you do get more torque.
But if you take like the same length of wire and then you loop it, isn't the side where
If you have the same length of wire, yeah, but what you need to imagine is if you were making the armature, you have like a big roll of wire and you just wrap it around many times and you cut it off. Like that's what you would be doing. I think if you increase the N, you can increase the turning force, but I think the price you pay is that the motor gets hotter. The wire gets hotter in it because you've made the wire. Do you remember the formula? Resistance equals rho L over A. So if you have the wire wrapped around many times, then the total resistance in the wire has increased. So if you have 10 loops, you've actually made the resistance 10 times bigger. which means then you're wasting, like you're probably making more heat energy. And if you have it wrapped too many times, then I think the wire would overheat and snap. So you can't just wrap it forever. There's some limit on this. Okay. The same goes with the eye. You think, oh, if I increase the eye, I get more turning force. That's true, but if you increase the eye too much, the wire, again, it gets too hot and snaps. Yeah? Okay, continue. Right, so we have I bands. Right. Now, remember that the flux over some region of space is the number of magnetic field lines. So 1 Weber, 1 field line. 2 Webers, 2 field lines, and so on. However, imagine now that the field passes through n identical regions. What's the formula for the total flux? So, okay, let's say we have one region here. I call this OR. And I have 1 field line through it. So what's my flux here? It's 1 Weber. But let's say my region is not just OR. Let's just call that OR1. Maybe that's OR2. And that's OR3. And let's just say they're all the same. So my total region is this and this and this. What's the flux now? Yeah, it's 3 Webers.
Yeah.
Although it seems a bit strange because it kind of looks like the same picture. But we're looking over more space. Like if I have one thing like this, and I have 1, 2, 3, that's 3 Webers. That's actually the same as if I have this. That's 1, 2, 3. I mean, this does not have to be connected. It doesn't have to be one piece. It can be broken. So you actually here you get 3 Webers. Anyways, my point is, that's actually quite common. Often we want to look at the field line through many pieces at the same time. And often these are all the same shape. So we have a special name for that. Usually for one piece we call it flux. But when we have several pieces together, we call it not quite total flux. There's
Fluxes.
Fluxes?
Yeah.
Oh, I like it. No. Do you want to try again? I'll be impressed if you knew it. It kind of means total. Fluxes? Fluxin?
Fluxes.
Fluxin? Fluxes?
Blunder.
Fluxin everywhere?
Flux
Flux bundle?
Yeah.
Getting closer actually.
Close.
Yeah, flux bundle I like. Flux lines?
Flux family.
Fluxin, flux lines.
Flux family.
Flux family. Flux linkage.
Oh, linkage?
Yeah.
What's the mean linkage?
So, the total flux, which is called the flux linkage, you just have to multiply, if you have 3 pieces, you just have to multiply it by 3. So in other words, if you have n pieces, you just multiply it by n. So the formula is quite simply n times the flux for 1. Or in other words, NBA, like the basketball. Because remember we said this is equal to flux over area, so flux is BA. So we have this formula here. Now, before you continue, let's write that. You can write this down.
Linkage means total flux.
Yeah, now it doesn't quite exactly mean that, but for this level of physics it can.
What does linkage? Linkage mean?
Total.
No.
Total flux.
No. Linkage.
I haven't written it down yet. AGE.
Yeah. Link and AG.
Well, the AGE makes it an adjective? No. Or noun? No.
Linkage.
What words end with AGE?
No?
Yeah.
Bombay.
Yeah, maybe something a bit more academic.
EAP come.
Voyage. Yeah, AGE makes it a noun, doesn't it?
Yeah.
It's a noun, yeah.
A is the area
It's the area, yeah.
of what?
One of the regions. So like,
One of them.
yeah, just yes, one of them. They should all be they're usually all identical, so these are all A's.
They were.
Oh, no, I don't think they'll do that in the exam. They've never done this in the exam. It becomes too difficult because then you have to calculate it for each one and add them all up. No, it should be identical.
So A is area in the region.
In one region, yeah. Link is a verb, to link two things together. So linkage is a noun. So linking all of them together into one.
Like combination.
Yeah, like a combination, yeah. Like a bundle, like you said, a bundle. Okay, now, what if the field makes an angle theta with the normal of the region of the space? Now, we have to be careful here with the angles, so let me just try and draw this. Okay, here is the field, B. And let's make it easy, let's just say n is 3, okay? And let's say here's one region, no, let's make it 4. 1, 2, 3, 4. Okay, what's the flux for one of the regions in this picture? 3 Webers. So what's the total flux? Well, that will be 4 times 3, yeah, which is 12 Webers. Okay. But in this picture, we usually imagine that the region of space is perpendicular here. But of course, like last time, we could have it at an angle. Now, this is how we measure the angle here. We don't measure the angle here. What we do is we draw what's called the normal. Can you see that? And here's the normal. And we measure it with the normal with the field. So in this picture here, theta is 0. And in this picture here, theta is not 0. So if I have a formula, total flux equals NBA, in this picture here, it's not NBA because I have to resolve. Yeah, so let me see. There's the B. So I need to resolve it this direction and this direction. So this is the cos and this is the sine. Which one do I want? The cos, the one that's perpendicular to the plane. So it's going to be NBA cos theta. If they're at an angle. Now the good news is you don't have to worry if it's cos or if it's sine, because in the formula book it gives both. So sometimes students can get confused. They're like, oh, which one was the cos and which one is the sine? Don't worry, both are in the formula book. Okay, so with Bill, you can have a sine theta in it, and with the MBA, you can have a cos theta in it.
You like that?
Yes.
Yes.
You like that?
Bill is full of sin, a sine. Yeah. Remember it like this.
MBA like what?
No, we'll have to think of something else than that.
How is that but that's perpendicular?
Yeah. How is this one the cos? Is it?
No, I know it's the cos because it's the cos, but it's not perpendicular to the thing.
It's hard. Oh, yeah. In this picture, what I've done is I've taken the magnetic field here, and this time I've resolved that into this is a bit like a BX, and then I put one this way, which is like BY, and this is still my region. And I only care about the field which is the perpendicular. Oh, hang on. Yeah, which is this one. Which is the BX, which is the cos.
You're resolving magnetic field?
Yeah.
Why do you want to resolve the...
Fine. So you want to resolve the region of space?
Yeah.
Okay. Well, let's do that. Okay, so. Well, you're still happy it's going to be MBA with a cos or a sine. Okay. So this is theta. So you want to resolve this? Of course you do. So we'll have to go. Oh,
Is this like...
no, don't please confuse me. Right, we'll have to go this way. No. Yeah, we'll have to go this way
Oh.
and this way, and this is the region here. So if we call this, I don't know. We'll call this L. Then this one here, if that's theta, this here is or let me call it A. Right, if that's theta, this is theta?
Oh.
Yes? No? Why is she doing this to me?
BA. Do not is BA.
That's theta.
BA. This is not B.
This is theta?
This is B.
This is theta, right? Because
Okay. B.
this is theta, so this is theta, right? Because this is what I'm thinking. If that's theta, then this is 90 minus theta. And if this is 90, then this is 90 minus theta. So this one has to be theta. So this one has to be a cos theta. So this region here is a cos theta. Same result.
Do they normally give the theta there?
No, they normally give it here. Yeah. Are you happy now? Okay, good.
This is good, I think.
It's definitely this.
This is like this, right?
I don't. Yeah.
Like,
Yes.
right, like
Yes.
we
Yes.
make this
Yes.
to- It's easy way.
No, why are you saying this?
It's easy.
Oh, fine. This is easier than my first one?
Yeah.
Yeah. Okay, whatever.
One more question now. You
Yeah.
changed this. Where's the normal now?
Oh. It's still here. Still here.
Ooh.
And it's perpendicular to
It's perpendicular to this plane. Here.
Oh, I got that.
This is the plane here. Yeah. She's because she made me change it.
Like this. Theta parallel to the field.
Oh, look, I'm getting tired of this, okay? Look, I'm just going to draw it, and this is the way I want it, okay? So look, here's your field. B, okay? Here's your region. Here, okay? Here, this is your normal. And this must be perpendicular to your space. And we measure the theta here, between the normal and the field. That's the theta. And the formula for the force, the flux, the flux linkage, total, is NBA cos theta. So if the theta was 0, it would look like this. It'd be perfectly perpendicular, and you would end up with MBA. So that's what it looks like. Yes, it's wonderful.
You didn't resolve
Which one?
the x and y.
Oh, I don't need to because I know I resolved it, and the one with the cos is the one I care about, and the one with the sine I didn't care about. Do you want me to put in the resolved ones? It was like this. You take your b, and it gets resolved into a direction which is this way, and this way. So this one here is b cos theta, and this one here is b sine theta. And because that is parallel to the space, we don't care about it. Because remember, for the flux, it's how many field lines pass through it perpendicular. So we don't care about the b sine because it's parallel. Can I continue? Yes? Yes? I'm continuing. Too much time on this. So anyways, the formula is MBA cos theta. And finally, the total flux is also called the magnetic flux linkage, mostly. Yeah. That's my, like terms and conditions apply. Technically it's not, but for this level of physics we can say it is. But if you were to be looking in a university textbooks, there's a small difference between flux linkage and total flux. But the difference is so small it's not important at this level. So flux linkage basically means total flux. Okay, got this formula?
Yeah.
Yeah, continuing. So, now finally onto some examples. A copper wire has 2 amps in it, and it runs through a magnetic field, and the copper is 20 centimeters long, and the field 3 Tesla. What is the force on it? Okay, which formula is that? Bill. And if the angle is 80 degrees, which formula is that?
Bill sine 80.
Yeah, okay, so calculate for me, please. Let's check it. B I L. First answer 1.2 newtons. Okay, and then the next one 80 degrees. Sine 80 1.18 newtons. Easy peasy?
Yeah.
Yep. Okay, next. DC motor is used to turn a wheel. The current is 3 amps. The flux density is 5 Tesla. The wire runs 1,000 times around a square of length 20. The square is attached to a wheel. What's the torque? Okay, so which formula is this? I-band. So calculate the torque, please.
600.
Okay, so I, B, A, N. Yeah? 600. What's the unit for torque? Newton?
No. Newton, meter, second.
No.
I-band.
Newton meter, yeah. Newton meter. Yeah. Okay. Continue. Next example.
Yeah.
Right, last example. A coil is wrapped around an iron rod. So let me just draw this for you. So you have a piece of iron. Okay. Radius 5 centimeters. And it's wrapped around 100 times. So you wrap it around 100 times. A magnetic field runs from the top to the bottom of the iron core. So you have a magnetic field running through the iron this way, and that is 2 Tesla. And my question is, what is the flux linkage? Now, what's happening here is you actually have lots of circles. Can you see that?
Yeah.
So I want to know what is the total flux linkage in the iron rod. So you actually have, you consider it as like 100 circles. So it's going to be NBA. Yeah, 100 times 2 times pi times r squared. So that for the total linkage, it will be 100 times 2 times pi times r squared. So that's 1.57 Webers. Yeah? Why is it not? What? Did I make a mistake? 100 times 2 times pi times r squared. It's okay? And lastly, if the angle is 10 degrees, so now if instead the magnetic field is at a little bit of an angle, well, yeah, what happens, I just multiply it by cos 10. .55 Webers. Yeah. Did you write that down? Yeah. Okay, so easy. Do you want, you can take a picture and then we'll
Finish.
No, you got 5 minutes to try them. Then we'll finish, okay?
Tomorrow we have
If that's what it is on the timetable, yeah.
What's the timetable?
because we don't have class on Friday.
Yeah.
We have 1 class. 1 hour.
Yeah, I don't have you on Friday. We have 1 hour tomorrow?
Yeah.
And the week after.
And the day after on Thursday?
On Wednesday.
Wednesday. Tomorrow.
Also, wow.
Not tomorrow.
What do we have on Wednesday? How many hours?
1.
And
Tuesday.
Tuesday?
1.
So we'll make the assessment support Wednesday.
And tomorrow is just the usual.
Usual class. Okay, can I close this?
This week we only have 4 hours for physics.
Yeah. I need a break from you. I'm getting too much time with you.
Not too much.
Not too much. It's not good for my health.
Okay.
Can I close it now? Or can I just stop the video?